Welcome to Brain Vision.
Hey everyone, this is question number 76 from chapter 14. In this problem, we're talking about physics students sitting in a lecture hall. We're given a heat output, the number of students, 50-minute lecture, volume of air in the room, heat capacity of air, specific heat capacity of air, air density, heat output during an exam. And then we're asked to find three things. Let's start with A, heat energy released in a 50-minute lecture. So this part's very straightforward. We just have to do we're given a basic equation. We're given how many students, we're given their heat output, and we're given the time. So that's all we have to do. So time here, 50 minutes, you have to multiply that by 60 to get it into seconds because we're working with watts, which is joules per seconds. So it's going to be 50 minutes, 1 minute over 60 seconds. Oh, I wrote that the opposite way. 60 seconds over 1 minute. So that's our conversion for time. And then how many students? 90 students. And then what our actual heat output is, which is 100 joules per second. That's watts, joules per second, times student. Can include that, times student, per student. And if you plug that into your calculator, you get 2.7 times 10 to the 7th joules. So that's our heat released. So now we move on to part B, which is temperature rise in the room during the 50-minute lecture. So temperature rise should have you thinking Q equals MC delta T. We just found our Q, we need our mass, we have C, and we're solving for delta T. So to solve for mass, we're not given it straight out in the equation, but we are given density and volume. So you can solve for that with M equals rho V. And if you plug in those numbers, 1.2 kilograms per meter cubed for rho, and then volume is 3,200 meters cubed. You get a mass equal to 3,840 kilograms of air in the room. So that's our mass, and now we can do Q equals MC delta T. We have everything now, and now we can rearrange that equation and solve for delta T. So delta T equals Q over MC. We plug in our known numbers. I'm going to do the bottom first to make sure I leave enough space. 3,840 kilograms. C for air we're given in the problem, 1,020. Joules per kilogram times K. And then Q, 2.7 times 10 to the 7th joules. And that gives us a temperature rise delta T of 6.89 degrees Celsius. So that's our answer for part B. Now we go on to part C. So C is if they're taking a test, what's our new temperature rise? And you could hypothetically do the full equation, but what you can recognize is that we have our two outputs, 280 watts over 100 watts. So this is during a test, and this is sitting. And everything else, the mass, the number of students, the heat capacity of air, that's all staying the same. So we can actually just set this up as a ratio. So this is going to equal our delta T during a test over our delta T during sitting. And then if you solve this equation for delta T, you just multiply this over. And that leaves us with delta T is equal to 6.89 degrees C times 280 watts over 100 watts. And that gives us a delta T of 19.3 degrees C. So whenever you're working with the same, whenever you only have one variable changing and you're given all the other information, keep in mind that you can do ratios like this.